Mathematical talk for today is from Faouzi Salem Thabet, de l'Université De Gabès.
Thank you.
And we talk about quadratic differential on the Riemann sphere.
Okay, thank you very much. So, it's great. Let me first express my gratitude to the organizer committee for this invitation. It's an honor for me to be here, really. I would like maybe take you far away from to another kind of relation. In particular, it's a case of horizontal and vertical trajectories of quadratic differentials on the Riemann sphere. Okay. This is the outline of my speech. The motivation is the so-called Foliations problem. And I think since we have two other talks in the same area, using the same area, quadratic differential, maybe it's convenient to give some basics from potential and quadratic differential theory. And I will show to, then we will see the connection between the Foliations problem and the quadratic differential via Lavrentiev and Golozin's theorems. And we will discuss the case of quadratic differentials related to the Foliations problem for the case of 3 and 4 points. Okay? In 1929, Chebotarev have sent a letter to Polya asking him the following simplified question. Given m distant points from the complex plane or even the sphere, find a continuum, a connected compact subset with minimal logarithmic capacity containing these points. So this is the so-called Foliations problem. So maybe what's logarithmic capacity? Here is some basics from potential theory. Given a compact subset, we denote by m of k, a compact subset. We define, we consider the collection of all probability measures supported on k. And for a measure there, we define its logarithmic energy as the integral of logarithm of 1 over absolute value of z minus t, d mu z, d mu t. And taking the infimum, we get what we call the energy of our compact k. And then we define the logarithmic capacity, or just capacity, by the exponential minus vk. And for Borel subset E, we define its capacity as the supremum of the capacity of all compacts included in E. Here are some formula. Of course, in particular case when Vk, the energy of our compact, is finite, then there exists a unique measure, which is called the equilibrium measure of K, where the infimum is attained. And we define also the logarithmic potential of this measure as the integral of the logarithm of 1 of absolute value of z minus t, d mu k, and it's characterized by this inequality and equality. For example, the capacity of the disk with radius r equals to the capacity of the circumference with radius r equals to r. And the equilibrium measure is d theta over 2 pi. For the segment AB, its capacity is given by absolute value of b minus a over 4. And this is the equilibrium measure of it. We have this formula for the capacity of sets. And be careful, capacity is not, it's not like measures, not continuous, not additive, and not subadditive. Now, it's a connection with our problem. Here, another version of the so-called Riemann-conformal mapping theorem, which asserts that given a subset E such that its complementary is simply connected domain in the sphere, then there exists a unique conformal mapping G from the sphere minus E to the sphere minus here, not the disk, it's the closures of the disk, satisfying these normalization condition, G of infinity equals infinity, G prime infinity is positive, and then G of z equals to G prime infinity, z plus something lower. Moreover, then what's the connection with the capacity? Here, the capacity equals to 1 over G prime of infinity. And of course, it's a connection also with the so-called green function there. Now we can reformulate our problem as follows. Given a finite set E formed by A1, etc., AM from the sphere minus 0. Find a conformal map called extremal map from the disk to C minus E, such that f of 0 equals 0, and absolute value f prime 0 is maximal. Maybe this, remember, for those who remember the proof of the Riemann conformal mapping theorem, you have something like this. Okay, here are two examples. The first one, the example of the segment, the Chebotarev, the Polya-Chebotarev problem of 2 points, A1, A2 is the segment A1, A2. The Polya-Chebotarev problem for m points, linear points here, is the maximal segment containing all of these points. And then the Polya-Chebotarev points for 4 points that are vertices of a rectangle depends on something. There is the height and the weight of this rectangle. On the left, we can see here in blue the continuum containing these points. In red, our points A1, A2, A4, A3, and A4. And on the right, the continuum of 2 square. Okay? Now, this is a definition of a quadratic differential on a given Riemann surface. In fact, here, as you can see, sorry. How to come back, please? Sorry.
It's just to come at.
Oh, yeah. Here is the definition of a Riemann surface, of a quadratic differential on a given Riemann surface. As you can see in the structure of our Riemann surface, we have a family of meromorphic function phi I satisfying this transformation law. Oh my God. Here. Okay. But let us put the feet on the earth and see what happens there. In fact, as an immediate consequence of this transformation law, any quadratic differential on the Riemann sphere is in the form of phi z d squared for some rational function phi. And to the best of my knowledge, here are two references from the theory of quadratic differential. The first one is the book of James Jenkins, Univalent Functions and Conformal Mapping, and second one, the famous book of Kurt Strebel, Entitled Quadratic Differentials. So now, given a quadratic differential on the Riemann sphere, given a rational function, non-trivial rational function, we define the critical points of our quadratic differential as the zeros and poles of this rational function phi on the sphere. We have two types of critical points. We have finite critical points that are zeros and simple poles, and infinite critical points that are poles of order 2 or greater. All other points are regular points from the sphere. Now, we define the horizontal trajectory, or just trajectory in the rest of my speech, of our quadratic differential as the level sets of the integral of imaginary part of the integral of square root of phi t equals to constant, which is equivalent to the fact that phi z d squared is positive. In the same vein, we define the vertical or orthogonal trajectory by replacing imaginary part by real parts and positive by negative. Okay, horizontal and vertical trajectory then produce a transversal Foliations of the Riemann sphere. Now we are interested in these trajectories. A trajectory of our quadratic differential omega phi originating from finite critical points from zeros and simple poles is called critical trajectory. If it starts and ends at finite critical points, it will be called finite critical trajectory or just trajectory, Now, we have to investigate. In order to investigate this trajectory, we have to see what happens locally and what happens globally of this trajectory. At any regular points, it's due to implicit function theorem, trajectories and orthogonal horizontal and vertical trajectory look like simple analytic arc, and they are orthogonal at this point. At the zero of multiplicity R, there emanates R plus 2 critical trajectories, and their spacing and their equal angle 2 pi over R plus 2. At a simple pole, there emerges exactly one critical trajectory. At a double pole, the local behavior of the trajectory depends on what we call the residue of our quadratic differential at this pole. More precisely, if we write our quadratic differential like this, a over z minus a squared plus something lower, then everything depends on a. We have three cases. In other words, there exists a neighborhood of our pole such that any trajectory inside this neighborhood should have one of the three possible forms, either the radial form, or the circular form, or the spiral form. Now, at a pole of order r greater than 2, then there exists r minus 2 directions. They are called critical directions. And there exists a neighborhood of this pole such that any trajectory entering to this neighborhood should diverge to the pole following one of these r minus 2 critical directions. Here, on the left, as you can see here, in green, it's a double zero, since we have 4 trajectories emanating from it. In the middle, we have a simple zero. We have 3 trajectories. And then we have a simple pole, just one trajectory. And here we have the local behavior of trajectory near a double pole. On the left, we have the circular form. It's when the residue is negative. And then the radial form when the residue is positive, and then the spiral form when the residue is not real. And here we have, on the left, we have the behavior of trajectory near a pole of order 5. Then we have 3 critical directions that should that we have here, that any trajectory entering to some neighborhood of this point should diverge following one of these 3 trajectories. And there we have a pole of order 6. So we have another type of trajectory, which is the case of what we call recurrent trajectory, which in the case where a trajectory with no limits from at least one of its 2 rays. In fact, a trajectory, if we follow a trajectory, we have 3 possibilities. Either a critical trajectory starting from a finite critical point, 0 or a simple pole. Either it should meet another finite critical point. In this case, we will call it a finite critical trajectory. Or it should diverge to some pole of order 2 or greater. Or, unfortunately, this nightmare case, it have no limits from at least one of its rays. In this case, we call it a recurrent trajectory. And this is the most known theorem which avoids the existence of such trajectory, which is the so-called Jenkins three-pole theorem, which asserts that no recurrent trajectory occurs for a quadratic differential of the Riemann sphere with at most 3 distant poles. But it seems that we can refine, there's a little refinement of this proof, we can get a more general result. In fact, if we consider the set of all critical points of our quadratic differential, zeros and poles, and we define an equivalence tracing as follows: any critical points is in relation to itself, and 2 critical points are in relation if and only if there exists a chain of trajectories, critical or not, such that we can go from the first point to the last point following these trajectories. And then we have this result: no recurrent trajectory occurs if and of course, I forget to define the multiplicity of an orbit. We define it as the sum of multiplicities of all critical points inside this orbit. In this case, no recurrent trajectory occurs for our quadratic differential if we have at most 3 distant orbits with negative or odd multiplicity. I don't know, maybe I show, this is the figure of a case of recurrent trajectory. A recurrent trajectory should be dense in some subdomain of the sphere. This is an example of recurrent trajectory. Now, what about the global behavior of the trajectory? In fact, these are the possibility of a critical trajectory. Now, since we said that from any finite critical points, there emanate a finite number of critical trajectory, and since we have a rational function of the sphere, non-vanishing rational function, then we have a finite number of poles and zeros, then we have a finite number of critical trajectory. If we consider the closure of the set of all these critical trajectory is called the critical graph of our quadratic differential. Also, it's called sometimes the Stokes graph of our quadratic differential. Then this critical graph Jenkins' theorem asserts that it splits the sphere into a finite number, this is not interesting, finite number of connected components that can have one of these 5 kinds of domains, configuration. The first one, we have what we call the half-plane domain. We have the strip domain, we have circle domain. These 3 domains are simply connected domain, and we have the ring domain, which is a doubly connected domain. Finally, we have the dense domain. It's the case of recurrent trajectory, the case when the trajectory is dense in some subdomain. Okay, of course, a quadratic differential, there exists what we call the associated metric here. And we can talk about geodesic of this quadratic differential. Okay. So what are problems related to quadratic differential? First one, the existence of short trajectory, finite critical trajectory, trajectories that connect two given finite critical points. Of course, the necessary condition is the existence of Jordan arc connecting these points, such that the imaginary part of the integral square root of our function phi equals to 0. But however, this condition is not sufficient, as we will see. How many of them, how many critical trajectories connecting 2 given finite critical points? And the case, the nightmare case, which is the existence of recurrent trajectory. And finally, the description of the whole critical graph of our quadratic differential. Maybe I will show you 2 examples. The first one, if we consider this quadratic differential minus d4 over z squared minus 1 squared dz squared, then as you can see, we have the origin as the unique finite critical point as a 0 of multiplicity 4. And we have z equals 1, exponential plus minus 2i pi over 3 are double poles with negative residue. And also we have another double pole with negative residue that is located at infinity. Just consider the change of variable y equals 1 over z. Then if we have, okay, of course we can avoid the recurrent trajectory using the theorem above. Then the critical, and using the fact that the critical graph is symmetric with respect to the real axis, here we can, and we have, of course, we are familiar with quadratic differential. We can get immediately the critical graph of this quadratic differential. By the other hand, from this relation, we see that the trajectories of our quadratic differential coincides what we call the lemniscate, polynomial lemniscate of the polynomial z to the power 3 minus 1. Of course, a lemniscate given a polynomial, non-constant polynomial p, then and a real non-negative, a positive number c, then we define the polynomial lemniscate of p, the set of all z such that absolute value of p of z equals c. In this case, we proved that the lemniscate, these polynomial lemniscate, coincide with horizontal trajectory of the quadratic differential minus p prime over p squared dz squared. Here, as you can see, in green, we have the polynomial lemniscate of our polynomial for c greater than 1. For c equals 1 in blue, it's the critical graph of our quadratic differential. And for c less than 1, in red, we have 3 connected components of our polynomial lemniscate. Now, if we consider the second example, the case of irreducible algebraic equation, we define the Cauchy transform of a Sagnet finite, compactly supported finite Sagnet measure mu. Of course, we know these properties of Cauchy transform, and we consider the following problem. Given an irreducible algebraic equation, p of z c squared plus q of z c z plus r equals 0, where p, q, and r are 3 polynomials, there exists a compactly supported finite Sagnet measure mu such that its Cauchy transform satisfies this algebraic equation almost every way in C. And the answer is then given by the theorem. If a solution mu exists, then any connected curve of its support coincides with a horizontal trajectory of the quadratic differential minus delta of z over p squared dz squared. where delta is the discriminant of our simple quadratic equation. And of course, the support should include all zeros of delta. We can find these results, for example, when studying the zeros, the distribution, the limiting distribution of the zeros of generalized orthogonal polynomials. Also, we will see this when trying to solve the Schrodinger equation, where, for example, a cubic oscillator, etc. Many cases when we have used this result. Okay, now coming back to our problem, remember that our problem is to find a continuum, a connected compact subset with minimal logarithmic capacity containing a finite number, our finite number of points. Then the first answer came from Lavrentiev, which gives basically what this theorem is saying is that the answer of our problem here is that the continuum should be something like this, like something like a tree, and the end point is, remember, we are looking for the polyattributive points, problems for our points A1, etc., AM. We are looking for a continuum containing these points with minimal logarithmic capacity. So Lavrentiev, what this theorem is saying is that the answer should be a tree like this, where the end points are our points AI. Okay? At this time, it seems that the theory of quadratic differential is not yet born, because it will be, I guess, found later by German mathematician Tegmüller in the 30s. And then comes the Gaussian theorem. Because, wait a minute, if we look at this tree as a possible critical graph of some quadratic differential. So it's obvious that our points, our quadratic differential is something like this. Here we have, just consider these arcs as a critical trajectory of some quadratic differential. In this case, it's obvious that our points AI should be all of them simple poles. Then we have something like this. This is the first thing. Also, we have other points. Observe here, what's this? We have, there emanate from this point 3 points. Here, of course, he considered infinity. Don't use it here. Here we have a zero, a sample zero, a zero from which we have three trajectory emanating from these points. Then here it's a simple point, B1, a sample zero. And here we have 4 trajectory emanating from this point. Then it's clear that we can look at this point as double zero. Then our quadratic differential here, z minus b1, z minus b2 square. This is square. Also, by continuity of the trajectory in the Hausdorff metric here, if we consider another point here, that it's clear that the trajectory going through this point should be something like this. And then we can, if we look outside this figure, we have the infinity is a double pole with negative residue. Then we get our quadratic differential something like this. And then here, what says Gaussian theorem? It says that there exists a unique monic polynomial p of degree m minus 2, such that the continuum, our continuum, the polyattributive continuum, coincides with the critical graph of the quadratic differential minus p of z over this stuff there. Okay? And of course, the function, the conformal map in G prime, G satisfies this differential equation here. Let's see some cases here. The case of the continuum of 5 points, symmetrically placed with respect to the real axis. Of course, from Gaussian theorem, there exists a polynomial of degree 3 such that the critical graph of the associated quadratic differential minus p of the product of z minus ai have one of these 3 forms, because since we have a polynomial of degree 3, then the first case we have a 0 of multiplicity 3. We have in the middle a double 0 and a sample 0. And on the left, we have 3 simple zeros. now we are interested in a general quadratic differential in this form. We can investigate the trajectories of this quadratic differential. In fact, we have only one finite critical point, which is u here of 0, a multiplicity of m minus 2. And infinity is a double pole with negative residue, and all the points a1, a2, am are simple poles. So we will discuss some particular cases of this quadratic differential. Of course, here we prove that no recurrent trajectory occurs for this quadratic differential, and also when u is varying in R, then any change of the structure of the critical graph of our quadratic differential should go through a case where either the rise or the loss of a finite critical trajectory. It's a very interesting result for us. Now, let's begin by the case, the simplest case, which is the vertices of isosceles triangle. Consider 3 points A1, A2, A3. A1 is the conjugate symmetrically placed with respect to the real axis. And under suitable linear transform, we may assume that A1 equals 0, A2, A3 equal exponential plus minus I alpha. Then Kuzmina theorem asserts that there exists a unique number C of alpha such that the quadratic differential, the critical graph of the quadratic differential minus Z minus C of alpha over Z times Z minus exponential plus minus I alpha, this is square, coincides with the continuum of our problem. This is the first theorem of Kuzmina. Here we have these pictures. Of course, it's not the unique case when the continuum is formed by 3 segments is the case of equilateral triangle. Now we consider the case of 2 real points and 2 conjugates, 2 real and 2 conjugates numbers. This is the Fedorov theorems. Of course, under suitable linear change of variable, we may assume that these points are 0 and C and exponential plus minus I alpha, where C alpha belongs to the interval 0 pi over 2, and C belongs to the interval 0 2 cosine alpha. In this case, we have the following result. Let alpha here and C. Then we have 2 cases for 0 from 0 less than C of alpha. Then the continuum of our 4 points coincides with the continuum of the triangle 0 exponential I alpha exponential my alpha. And we come back to the Kuzmina theorem, the last theorem. For C between C alpha and 2 cosine alpha, then there exists a unique real number U, which is given explicitly by means of some elliptic functions, which equals to B of depends on C and alpha, such that the critical graph of this quadratic differential, Z minus U square over Z times etc., coincides with the continuum of the 4 points 0, C exponential plus minus I alpha. Okay, here's some measures. The first case here, when 0 less than C less of C alpha, and we have on the left, on the right, the second case. Okay, we can generalize this result for m points and 2 conjugate real number. We get the same result. And also, here we are interested on the existence of short trajectories of our quadratic differential. In fact, we prove the existence of this trajectory in many cases. In fact, there exists 2 points trajectory emanating from U and going to exponential plus minus I alpha. We prove that there exists 2 real numbers D1, D2, such that we have 2 short trajectory connecting these points to exponential plus minus I alpha. Here are some pictures. As you can see here, always the red points is the simple poles, and the in green is the zeros. Okay? This is another case of trajectories connecting U to the poles, our simple poles. Now, let's come back to the main result of our work, which is the case of symmetric trapezoid vertices. And under suitable linear change of variable, we may assume that our points are exponential plus minus I alpha, exponential plus minus I beta. And the sequel, we consider this begin by our lemma, this quadratic differential minus u minus z squared over q alpha beta of z. Q is the polynomial z minus exponential plus minus I alpha times z minus exponential plus minus I beta. Then we give first the border of the critical graph of our quadratic differential here. In fact, we prove that the quadratic differential here, q alpha beta u, is bordered by something like this. Either we have three possibilities, either something like this, here our simple poles, or something like this, here are simple poles, or something these are all possible configuration of the critical graph of our quadratic differential. But we forget another interesting case, which is our case. We want to answer the polyattributive problem, which is the case of maybe something like this, or we wanted to investigate the possibility of existence, or the last case, of course. These are all possible configuration of the critical graph of our quadratic differential. You have time? Just the result, the main result. In fact, we prove there exists for any beta, there exists a unique alpha of beta such that the continuum of such that for beta, for any beta from 0 to pi over 2, there exists a unique alpha of beta such that we have, for alpha belonging to the interval beta, alpha of beta, we have the case, we have the continuum should have this form on the left. For alpha equals to alpha of beta, we have the X form here. The Chebotarev problem has the X form. And for alpha, between alpha of beta and pi, the Chebotarev compact have this form of X, reversed X. Okay, thank you very much.